afternoon. My name is Hafiz Sheikh. I'm the business head for Manufacturing Today. On behalf of ITP Media, Manufacturing Today, and Husky Injection Molding System, ladies and gentlemen, I welcome you all in today's webinar. The theme you know, the topic you know, an in-depth look at color change performance, new hot runner technology to optimize color change, procedures, and the impact on production cost, time, and output. Our partner for today is Husky Injection Molding Systems. They're the world leaders in injection molding system. In the fast-paced world of technology changes, companies are expected to keep abreast of new development in order to stay ahead. Having the latest information and technology know-how ahead of others can change the course of your growth in this competitive world. In today's webinar, industry expert from Husky will provide an in-depth look at molding application and demanding color change requirement. ITP Media Group publishes more than 100 weekly and monthly magazine, has a wide portfolio of market-leading digital properties. We also organize more than 100 business and consumer events, conference globally every year. ITP India produces a wide range of business-to-business publication, websites, awards, program like this, the one which we are conducting, and information services for key vertical markets in India. As you can see, our portfolio includes hospitality, architect, manufacturing, construction, healthcare, media and broadcasting, and many more. Each of ITP India offering are dedicated to provide its audience with critical information and essential business insight, which in turns help organizations across the region to run and grow their business more effectively. A quick on Manufacturing Today. Manufacturing Today is India's leading magazine, which focuses on people, process, and technology for large and mid-sized organizations. Our partner for today, Husky Technology, is a leading industry technology supplier to the plastic process community. The company design, manufactures, and service the industry most comprehensive range of injection molding equipments, including machines, mold, hot runners, auxiliaries, and integrated system. Husky equipments and service produce a wide range of products for beverages, food and packaging industry, medical industry, home care, beauty and personal care, automotive, and consumer electronic. Husky has more than 4,000 people worldwide, and its customers over 100 countries. With this, I would like to introduce our speaker for today, Derek, who's the product manager, hot runners for Husky Technology. Derek is currently responsible for new product launches, specialty applications, and product portfolio management. With over more than 20 years of experience in manufacturing and plastic application, he specializes in hot runner technology and injection molding. We also have Mr. Rajan Kasi. He's the Vice President, Southeast Asia, hot runner controller and Husky injection molding. Years of experience in the mold, tooling, and process industry. He has a wide role of supporting customers, audience, value to client manufacturing processes in several countries. Rajan holds a master's degree in engineering from University of South Australia. With this, I would not like to hold more. I would like to go to Derek and requesting Derek to start his presentation. Over to you, Derek.
Thank you, Hafiz, and hello, everybody. It's great to be here today. Thank you for having us, and let's get started. From the outside, color change may seem simple and have little relevance to production or manufacturing. We just replace the old color with the new color and keep making product. How hard can it be? Of course, it's not that simple. Material must be cycled through the melt delivery system, replacing material of one color with material of another color. While it would be great to replace the color in a single shot, this is highly unlikely. Downtime and scrapped material are a fact of life when it comes to changing color, and it is a necessity for the meeting of a quality requirement for a specific customer or a specific brand. A poor color change process can result in extra waste material, a high amount of downtime, and increased scrap. These can accumulate to higher production costs. Today, we'd like you to take away 5 things. First are the design principles behind hot runners and color change. Second are how those principles relate to hot runner design elements. Third are the benefits of color change sequencing. Fourth we will discuss new technologies outside the hot runner and how they apply. And finally, we will talk about a couple of case studies. The first principle of hot runner color change is about minimizing volume. Like the cartoon shown here, small things are easier to move than big things. When it comes to hot runner color change, the thing to move is the previous color's volume of molten plastic inside the melt channels. If this volume is small, it is much easier to displace than a larger volume. The next principle is eliminating or minimizing dead spots, also known as no-flow areas or stagnation areas. A visual way to consider this is with the surface of a road. If the road is smooth, rain quickly and easily runs off the surface. But if the road is rough and full of bumps and holes, rain can pool and collect, causing slow and long-term damages and deterioration. The hot runner is the road the melt follows from the machine barrel to the cavity. The bumps and potholes in the road represent these no-flow or stagnation areas in the melt path. Old color may snag or hide in these no-flow areas where it can eventually stagnate and degrade. Old color in these areas may unexpectedly burp or bleed into the melt stream during production of the new and different color, causing scrap. It may require an increased effort or process changes to scoop out that old color, extending downtime for the changeover. So this isn't just about melt channel quality, it's also about managing the flow of that melt. So the final principle is to follow a procedure and set expectations. It's important to understand these expectations, and it's known that many variables affect color change, which can affect the ability to meet that expectation. Process settings can help color change tremendously, so it's important to know if they can be changed. Designing a specific color change schedule and procedure can directly manage the ability to meet those expectations. For example, we wouldn't expect a 5-minute color change when dumping a bucket of white material into the hopper that's half full of blue pellets. So unless we've seen it happen before with that same exact work cell and those conditions. Now we will talk about how these principles apply and how they influence hot runner applications and designs. Our first influence is the control of gate bubble volume. This is affected primarily by the nozzle size and the gating style. The gate bubble is the volume of plastic surrounding the nozzle tip between the nozzle tip's seal ring and the gate orifice. While processing, this area is neither completely solid or completely molten. The resin contacting the gate steel is cool and solid, which acts as an insulator, but the resin closer to the heated nozzle tip is hotter and molten, giving the flow path from the nozzle to the cavity. The exact properties of this bubble and its cross-section are heavily dependent on the application and the resin. The design of the bubble may have a stagnant or backflow area. This aligns with our bumpy road principle, where color in no flow areas can be difficult to replace and can extend color change time. The gate bubble and its effect on color change can be managed with a tip insulator. This part is made from a relatively soft material that can withstand a relatively high temperature. This applies our reduced volume principle as it replaces and reduces the molten volume in the gate bubble. It also eliminates the stagnant or the backflow area. A gate bubble is nearly unavoidable, but certain nozzle tip designs discard or zero out the gate bubble by sealing at the cavity interface. This also follows our reduced volume principle by eliminating the gate bubble altogether. With this gating style, no tip insulator is needed because melt flows directly from the nozzle into the cavity. Our next influence is manifold design. This applies to any hot runner, regardless of nozzle, or gating style. When considering color change and the manifold's design, the key principle is volume control, and the greatest design influence on volume is melt channel diameter. Shear rate is sometimes quoted to have the greatest influence on color change, but it's important to remember where shear rate comes from. Its first two influences are part weight and fill time. These are application requirements. Part design dictates weight, while part geometry and resin properties dictate fill time. These are not controlled by the hot runner. But shear rate is also dependent on melt channel diameter, which is directly controlled by hot runner design. While tip insulators or tip choice can be used to minimize volume at the gate, melt channel diameter in the manifold has a very strong influence when designing for color change applications. Since shear rate is not a true unit of measurement, we can view it as an effective rating for the color change performance in that channel or component. Finally, a hot runner design must also consider the pressure requirement of the application. So while volume or melt channel diameter should be minimized, it should not be reduced so much that the pressure exceeds the injection pressure limit of the equipment. So having an excellent color change can't help anybody if the cavity cannot be fully filled and packed out. Of course, the application or the part itself has an influence on performance. Part weight has an especially strong influence on color change. This is because as part weight decreases, shot weight increases, and as shot weight decreases, color change speed decreases. This is because there are two volume attributes for a hot runner: shot volume and melt volume. Melt volume is specific to the hot runner and is measured in units like cubic centimeters or cubic inches. It is the result of melt channel diameter and mold layout. This is purely geometric and stays the same no matter which press, which part, which mold, or which resin. Shot volume is application dependent. This is determined by part weight and mold cavitation, which combine to make the shot weight. It is also directly related to the hot runner's melt volume. For example, let's consider two different molds using the same hot runner. The mold making larger parts has less shot volume, even though the melt volume remains the same for each mold. This is because it's the same hot runner, and the greater shot weight consumes a greater portion of that melt volume. It's important to remember that just like a mold, a hot runner is limited by the laws of physics, thermodynamics, and finance. The tooling for a small diameter melt channel typically has more limitations than a larger melt channel. This is due to availability of feasible and affordable tooling, which can truly be built and meet the application requirements. This can also limit the access of extrude hone material used to deburr and polish the melt channels. In other words, every design is limited by its ability to be manufactured. It's useless if it cannot actually be built. Another factor to consider when designing hot runners for color change is the manifold's thermal profile. The thermal profile is optimized by adjusting manifold shape, heater wrap, thermocouple placement, melt channel layout, and load-bearing components. Their combined effect is confirmed and validated by finite element analysis, which ensures minimal thermal variation. In addition to injection pressure, a uniform thermal profile will minimize cold regions along the melt's flow path. In these cold regions, the thickness of the plastic boundary layer at the melt channel wall can increase. This increased thickness can act as a relative dead spot or stagnation area to cause difficulty when changing color. So to minimize risk Husky confirms every manifold design's thermal profile. While our first two influences on hot runner color change covered application and design, how the melt delivery system is built also has an influence on color change performance. Specifically, this is about minimizing variation. One way to minimize variation is by automating the heater install. This ensures consistent performance from each heater and each zone. This can be important for high cavitation molds where multiple manifolds with the same design are used. This also ensures consistent expectations if the hot runners are swapped in a fleet of molds, or taking comfort in knowing the hot runner performance will be the same before and after a preventative maintenance. In addition to resistance checks and power testing at final assembly, another option is to validate manifold heaters by using thermal imaging. This is periodically used for audits and troubleshooting. Manufacturing has its greatest effect on the second principle, which is minimizing the dead spots or ensuring a smooth melt flow path. When resin is not flowing, it's stagnant. Not only are these stagnant areas hard to displace, but stagnant resin can degrade over time. If a colorant is sensitive to heat, this can present a challenge to production quality. One of the ways we validate this is by measuring and comparing the degradation of sample parts from manifolds with various build conditions. We tested these manufacturing influences by building several manifolds with different levels of variation, running color change procedures, and comparing their performance. The results showed by applying our principles, gating, and minimizing manufacturing variation, we achieved the best color change possible. Among our principles, the third and final is to set expectations and to create a procedure. This is one of the most effective ways to execute color change. It is immediately controlled by the production schedule, the operator, and the equipment on the production floor. The order of colors changed has a substantial impact on resin usage and downtime. It helps to consider which colors are most closely related and even establish which have the shortest turnover time through testing. If this information can be utilized and the flexibility is available, production scheduling can take advantage of both to maximize productivity. Here, we show a production run that was not optimized for color change. To complete a full color change cycle, 600 shots or 127 pounds of material were needed. So here we can see a couple of the same color. This is to represent haphazard or random planning. But by just changing the run order of these colors and to minimize the change time between color, the changeover was reduced from 600 shots to 400 shots. Wasted material was reduced from 127 pounds to 85 pounds. This was a savings of 33% in both downtime and scrap material. By taking this consideration in the production scheduling, this takes advantage of a best practice and is a great example of applying the procedure principle. On top of hot runner design considerations and scheduling, other technologies can be leveraged to decrease color change time. So far, we've shown changing color does not hinge on a single set point or a single asset. By taking a system-based approach to include the molding machine and the hot runner temperature controller, consistency and efficiency can be improved further by utilizing purging compounds, which are best discussed with an appropriate supplier for your application. Husky worked with one supplier on a system solution to include processes in the temperature controller's operator interface. This gives work instructions that are consistent and immediately available. By having instructions in a centralized location and automating certain steps can also reduce scrap and downtime. Using Husky's ALTANIUM controller and its touchscreen monitor, color change instructions can be integrated into the ALTANIUM software and give precise guidance at the operator's fingertips. Features such as soak timing and automatic temperature adjustment, coupled with cycle count input from the molding machine, can ensure correct steps are followed every time with automated procedures. This delivers consistent and optimized results, no matter the machine or the experience level of the operator. So now, let's take all those principles and concepts and see their impact on some real-world examples or case studies. In one study, we saw a 32-drop polypropylene closure mold where changing from amber color to natural was reported to need up to 9,000 cycles in 28 hours until an approved part of acceptable color was produced. This may sound outrageous, but we need to remember that for many large brand owners and OEMs, color represents a specific part of their product brand and is a product differentiator. So what I'm trying to say is that companies can be very picky about color. Considering this, we implemented adjustments and solutions which reduced that changeover to 215 cycles in 40 minutes. Not only did this save over 22,000 pounds of scrap material, but it saved more than 650 hours of machine time. That's almost the entire month of February. This not only represents significant cost to the molder, but was also a significant point of frustration, which can happen regularly in our industry. In another case, we reviewed a 2-shot mold with 8 cavities. This used 2 different grades of polypropylene. This mold also had a high color change frequency. Its most demanding change was from black to white, which is always one of the most challenging. It required 1,100 cycles to make this change. With review and solution, this was reduced to nearly a quarter of the original time at 240 cycles. This saved over 5,000 pounds of material and 150 hours of operating time per year. So from these case studies, we can see the value of a high performance color change. So we hope today that you've learned and gained an appreciation not only for the importance of color change, but for all the considerations needed to make it happen, such as design principles, application influences, and the importance of color sequencing. Thank you for your time. I'll be happy to take any questions, either now or if you feel like reaching out in the future. Back to you, Hafiz.
Derek, thank you very much. I would personally, it means a lot. You are in Canada and it's 5 a.m. over there. Really, thank you and your commitment to share your best practices from Husky. Yes, we do have question, and I'm sure you would like to also answer those. We have a few offline questions that I would like to start with. If anyone from the audience would like to ask any question, happy to take that. First question, Derek, are there certain reasons that are harder to process when it comes to quick color change results?
Sometimes what can happen is with high viscosity resins, they may have a high shot volume or a high melt volume because they have larger melt channels. This will be a bit different from resins with low viscosities. This way we can have smaller melt channels and smaller volumes to replace that material. So yes, certain resins can be more difficult to process. There's almost always a way to optimize that color change.
Thank you. Thank you, Derek. Would like to take another question. Is system or hot runner balance connected to color change results? And any example that you would like to, with a case study, would like to give?
Balance can affect color change, especially if the balance is poorly designed. For systems with poor balance or with poor geometric balance, those cavities and those melt paths, which have more residence time or more length, can be more difficult to change color.
Appreciate. I third would if I can ask you, can your ALTANIUM controls with ultra purge technology be used on non-Husky machines?
Yes, because the controller can be moved from machine to machine. It has flexibility, and those ultra purge technologies can also be transferred because they are not specific to any one machine.
Is the color change process more difficult on high cavitation systems?
Yes, it can be. This is because high cavitation systems are more complicated. They have more details compared to a low cavitation system. For the same part, there will be more melt volume to replace, so more cc's of resin to wash out and replace with new color. And there will also typically be a little more shot volume to replace that color.
Derek, the last one, what would be your recommendation? Either change color directly from one to another, or to use flushing compound, which ultra purge for HDPE can injection with hot runner system, and why?
That's a good question, because there are a lot of different things that can happen for a system like that. The resin type or the viscosity can have some effect. So can the colors that are being used. Are you changing just from one color to another color and that's it? Or are you molding 12 colors? And also, what are the procedures that are currently being used? And what is the expectation? So there are so many different facets and so many different influences to that situation that it will always depend. But one of the best ways to find out is to run some experiments, establish a baseline, speak with a hot runner supplier to understand the technology and the options available, and also to run some experiments with purging compound to see not only if it can be done, but how effective it is. Finally, an analysis or an understanding of what's needed. If you need to make a very fast color change every 2 months, maybe that's not as necessary, or maybe that's not as helpful with a purging compound as if you were to do 5 color changes a day. That's there are many different things to look at, many reasons why or why not. But if there is any advice, that's how I would advise to start considering these things.
Rajan, if you would like to add anything on the question that
Yeah, so I think you have asked a couple of good questions. So one is that the ALTANIUM controller, how it helps on the ultra purge as well as the color change, especially the machines as well as the non-ASCII systems. We could experience to see like many of our customers, which is having a old hot runner system, and like overnight they can't change the brand, but when they face the problem, like we trying to provide them the controller, which ultimately works, because the one of the area where Derek brought up, the balance is very key for making a better color change and faster. These ALTANIUM actually play a very key critical role to maintain the temperature. Like in our controller, it's a kind of a auto fine-tune PID setting, which means that it doesn't matter what controller you have, what hot runner you have, what kind of the wattage you have, it sets automatically their value, and it hit up the same, and it control within 0.5 degree at the mold area. So that's one of the key point where it really helps even for a non-Husky systems. So that's one area. And the second, the question which you asked about the high cavitations and the HDPE material color change. That's one of the critical area where we do play a role at the initial stage and also the qualification stage. Like the initial stage, I think I have been here like last 10, 12 years. Like we are the very, very tough guys for a mold designer or the project people at customer, because we are asking so many detail, like we are the only company asking, the HTB, what's the grade to find out the mold flow, and how it's going to be color change. It's like a weekly or daily, monthly. So all these, the initial information, it's very much going to be help us to design the best application for that particular product, because we're proud to say that each and every harness system coming out from Husky is completely application based, designed and manufactured system. So it's always we used to tell to the customer, guys, you are paying for a product which is particularly for particular application, so why don't you give more information so that we could able to work more, precise the channels, precise the material resistance time, precise the pressure drop and shear rate, so that would be going to be work for a lifelong system. So that's why, because Husky play a big role in high cavitation packaging, closures, and especially the healthcare, where the system's going to be run not like a short period like 2 years, 3 years. So we love to work with the customers and partnering with them, especially when coming to this kind of the application solutioning at an early stage. And also the changing the color, we have a multiple process and a procedure to do that. And all our engineers are qualified for that to transit that qualification into the production technicians or production managers, so that they could be able to do the day-to-day activities. That's all what I found these two areas, which I just want to update you guys. And we love to hear because we are here and we are getting more and more challenge application, and we love to be challenged, and then we are success on it. Thank you.
Thank you very much. Thank you very much, Derek. Thank you, Rajan. Very much. We would like to conclude this webinar, and I would like to say a big thank you, Derek. It's 5 a.m. Again, I'm saying, you're joining from Canada. Thank you, Rajan, for your insightful, answers.
Yeah. Derek is committed like our hot runner, like.
Correct.
So don't worry, we get this stuff. Thank you.
Yeah. I personally feel the session was very filled with insight. Derek and Rajan, thank you very much for sharing your experiences. We appreciate any commitment and dedication in sharing insight in the interest of the manufacturing industry in India. Additionally, thank you everyone from the audience who made it for this, and people who have registered for this. We will be covering the next the entire report on our next issue, and also the video will be live on our website. We're going to send this entire link to you, and we look forward to have another session very soon. We hope it was a learning experience for everyone. Each stakeholder of the summit, from this speaker side, Husky, and from the audience. Thank you very much, and have a best time and be safe. Thank you.
Thank you. Happy.